So 802.1.x requires login authentication before even allowing access to layer 2. 802.1x can also be applied to network switches for device access to layer 2 after it plugs into an Ethernet port. So it's the protocol is not limited just to wireless applications. 802.1x uses 3 devices to participate in the authentication. It's got the supplicant, which is generally the client or the computer that's trying to connect to the network. The authenticator, which is generally the access point that it's directly connecting to on the wireless, and then the authentication server that holds on to all of the user credentials and validates whether a user is or is not allowed to access the network based on a username and password. So the way it works, the supplicant requests access by sending his authentication credentials to the authenticator. So, computers wants to get on, sends those credentials to the access point that he's most closest to. The authenticator access point sends these to the authentication server, which checks them against the database and lets the authenticator know if the user is allowed access. If the credentials don't match, the user is either completely denied access or is given severely limited access. If the device does pass authentication, the supplicant and authentication server generate a dynamic encryption key known as a session key. This provides the same security as the preshared key, but does not require you to enter a preshared key on the client or wireless access point. So it saves you that trouble of manually configuring the PSK on each device like you would for web encryption. Keep in mind that we're referring just to authentication in this case, not to encryption. And then the other thing to keep in mind for wireless security is setting up a wireless intrusion prevention system, or an IPS. An IPS for wireless specifically is you've got IPS used for other applications, but a wireless IPS is used to detect rogue wireless access points on your network. So if an employee that shouldn't be hooking one up tries to hook up an access point somewhere in your building, you'll be able to detect this. Or if maybe you've just got an adjacent business that they've got some wireless leaking over to your side, it'll give you some kind of indication of this so that you can adjust accordingly. It can analyze signal levels to even pinpoint on a map where the rogue device is physically located. There's a lot more about this on the CCNP, but the tools for the IPS are actually really cool, like as far as mapping out like your full network, showing where all the access points are, and then really being able to, within like about 10 feet, tell you where any kind of rogue access points are located at. So wireless topologies, and we kind of briefly touched on this a little bit in the last chapter. This covers the deployment of access points, their locations, and the setup. It can be deployed in 2 forms, ad hoc or infrastructure. Ad hoc uses an independent basic service set, or an IBSS topology. Each wireless device manages the wireless network independently. It's generally limited to devices with a short range, like a laptop to laptop, for example. If you're connecting to like a Bluetooth device through your laptop, that would be an example of an ad hoc network. So it's kind of a limited set of conditions where you're actually going to mess with this. Then the other option is infrastructure, which is your more common wireless network in homes and business today. Uses dedicated equipment to manage a wireless network, generally a wireless access point. It can be deployed as either a basic service set, a BSS, or an extended service set, an ESS, which basically means how many access points are you working with and whether you can roam between those. So for a basic service set, you're only going to have a single access point that any of the devices can connect to. There's no roaming allowed. There's no other devices to potentially peer with. You've got a single device, and you've got the limitation of the range with that. So that's a BSS. For the extended service set, though, you've got multiple, much like the honeycomb mesh grid we saw in the last chapter. You've got multiple access points with different channels next to each other. Again, generally you want to have about 10 to 15% overlap on these channels to ensure that roaming happens. And the access points have to use different channels, or you'll have a lot of interference right here at the areas where they do mix. Now keep in mind the overlap, it's important for any well-designed wireless network, but for the most part it's not really going to have a whole lot of impact on individual laptops and that kind of thing. This is mostly important for cases where you've got, say, wireless IP phones, where if you lose signal even for just a second, you can drop a call. A laptop that's sending and receiving data on a per request basis probably is not going to be nearly as affected by that. But you still want to make sure that you go through the correct design procedures of setting some overlap between the two. And then something else to discuss is the wireless data rates. First of all, the advertised data rates are only theoretical, and you won't actually see rates that high. So all users, so you're not going to see rates that high. So what they do is they do a step method to kind of give you an idea of like how much speed you're going to get based on how far away you are. Now there's no so right here you've got the steps set out for 802.11b. There's no like set distance on 5 feet from this access point you're going to get this speed, and 10 feet you're going to get this access point, or anything like that. It's based on a variety of factors that can change at any time. It's going to be based on how strong the signal is coming out of there, what kind of environment you have, are there devices or furniture or anything in the way, are there any reflective surfaces or any of the things we talked about in the last chapter that can cause the frequency waves to bounce around or be blocked by like concrete, something like that. So this is just like a general guideline to realize that the further you get away from the access point and the more stuff you have in the way, the slower the speed you're going to get. And even for 802.11a and G, the expectation is that it can do up to 54 megabits per second. But in reality, like you're just not going to get that. Even if you're sitting 2 feet away from the access point, you're not going to get quite those speeds. There's still ions in the atmosphere that are going to block some of that you're not going to get quite the speed advertised. So that's just a theoretical, scientifically potentially possible rate, like in a vacuum somewhere. And the other thing to note is that if you have multiple users connected to an access point, all users are going to get the speed of the lowest speed of the user on the network because of the nature of CCNA collision avoidance. So if you've got most of your users hanging out over here real close by, but you've got a single user way back here that's only going to get 1 megabit per second because he's so far away and there's stuff and furniture in the way, all these other users over here are also going to get that low speed of 1 megabits per second. So that's a real big reason as to why whenever you set up a full mesh, you've got multiple access points and a little bit of overlap. That way, if you try to set a building up with just a single access point, you have really degraded signal at the far outreaches, but you still have users connected out there, you're going to have some pretty bad network performance as opposed to setting up multiple access points with different frequency range or with different coverage ranges.
Find the guy that's on the edge and beat him up.
Well, yeah, pretty much. Like he's going to be bringing everyone else down to that lower speed, so you need to either redesign so that he's on a different access point or do something else so that the other users can enjoy the full benefits of wireless.